Now to the third exercise, which finally starts using some dynamic memory. This third exercise is a great exercise to see if you've understood whatever has happened in this course up until now. It's a simple, well, not too simple, it's a relatively simple exercise, but it's a tedious one, it can take some time, but it tests almost every concept that we've seen in Risk 5 up until now. So this is a typical type of exam exercise. You could expect this type of exercise on your exam. If you haven't solved it yet, I suggest maybe you try solving it first. It's a great repetition exercise. But let's discuss a solution. Maybe you got stuck, or maybe you just don't want to solve it yourself. You will learn less by simply looking at the solution, but okay. So, some clarification first about the assignment here. So probably we're going to update this to make it a little bit more clear, because we got a few confusing questions about this stack structure. So the question is going to be, we're going to implement a stack data structure on the heap. The heap, like we explained in the video, or in the presentation, we have here a big heap reserved in our data section, and we have this global pointer that points to the next free byte in this region. And then we have this allocation function, which we will use to actually allocate space on this heap. Okay, so now we are asked to use all of this to write a stack. Now, first confusion. Some students are confused here because we're creating a stack, but in the third exercise session we also use the stack, and we already have a stack. We have the stack pointer. Now let me make clear, these are two very distinct things. On the one hand, you have your call stack, and this doesn't change. You have your call stack, and whenever we create a function, we are going to back up certain registers on the call stack. The call stack is a stack. Every process has this stack. That's not what we are asking to implement here. A stack is simply a data structure. The call stack is an example of a stack. But we want you to implement the general stack data structure. And how does a stack data structure work? Well, let me quickly open a notepad. Wow. Okay. So, let's say you have an empty stack. Okay, then you push an element 1. Then you push an element, so then you are going to have the top of the stack pointing to 1. Then if you push an element 2, the top of the stack will point to 2. If you push an element 3, the top of the stack will point to 3. So this stack was obtained by pushing 1, 2, and 3 in that order. And what makes a stack special? What makes it different from a list? In a stack, you don't necessarily have an option. It could be an option, but you don't necessarily have an option to look at anything else than the top element of the stack. The most default stack operations are push, as we now explained, and pop. And with pop, we remove the top element from the stack. So what happens if we pop something from this stack? Well, then we remove this element, we return this, and top now points to the 2. And if you pop again, top now points to the 1. Whoops. Like this. So you have a stack, and you can push elements and you can pop. You can imagine this as a stack of books. You start by placing one book on your stack and then another book on your stack. And if you remove a book, well, what are you going to get? That's the last element you put on the stack, you get that back. So it's a term, it's also called maybe a LIFO queue in a sense. You can use a stack to implement a LIFO, last in, first out queue. The last thing that entered is the first thing that gets out. So that's a stack. And this is a representation of how you can create a stack in your memory. So you these are the stack elements. You have 3 different elements of the stack. And what you could do let's say these 3 elements, these could be located at completely different regions in your memory. But how are these regions connected? Think about the presentation, think about linked lists, for example. How are these connected? Well, let's say now the address is the line number. So I would say the line number of 2 is 3. So let's store the address next to the value on the stack. The line number of 1 is 1, so let's store the address of the next value here. This one doesn't have a next value since it's the bottom element on the stack, so let's store 0 here. So we store 2 values for each element. The value itself of the stack element and also the address of the next element. Then we also need to keep track of what the top of the stack is. And that's why we have this top pointer here. We could write this differently. We could write here top points to 5. Line 5 has our top. So that now we have here this nice stack structure. And that's exactly what's visualized here. So each of these squares are 32-bit regions on our heap. This is a stack with 3 elements. The element 1, the element 2, the element 1. 1 to 1 on the stack. If we pop from the stack, we remove this first square, the 1, and top points now to this square, the second one. If we add an element to the stack, well, this element will be inserted right here where my mouse is. That's where this element will be inserted. So the next pointer of the new element will point to 1, which is the old value of the top pointer, and the old top pointer will point to the address of this new element. So all of these squares can be at any random spot in memory. They just need to be connected using addresses. That's how dynamic structures work, remember from the lecture. Enough introduction, let's look at the stack create function first. So when we want to create a stack, an empty stack, think about of this image, what needs to exist for an empty stack? Well, only the pointer to the top. But it's empty, so there is no top yet. Exactly, that's why we will store. An empty stack will be represented by a null pointer. So we will store 0 in this top. So that's what this function does. The function allocates enough heap memory to store the pointer to the top of the stack, this top square. This square here is located somewhere in memory, right? This memory location contains a pointer, but it also has an address. And so that's the address of our stack. When we say the address of our stack, we say this is the address of this top square. So, since the stack is empty, we're going to store 0 here in the value top. This is a pointer to nowhere, the null pointer. And we're going to return the address of the top pointer in A0. So of course we're not going to return the value of the pointer, which is 0. We're going to return the address of the pointer, which is somewhere in the heap, if you allocate this correctly. And that's going to be the address of our stack. So whenever we pass on the address of our stack, this will be the address of the top pointer. And this is what stack create will now create for us, this top pointer. So let's now look at stack create. What does stack create do? Well, first of all, stack create will need to reserve 4 bytes, or 32 bits, or enough space to store a pointer. So how does it do that? By using this allocation function. Allocation function takes the amount of bytes to reserve in A0. So that's what we do here. We reserve 4 bytes on the stack. Now, this is a function call, a nested function call. We need to store the stack pointer, the return address on the stack, on the call stack. This stack has nothing to do with the stack that we're implementing now. Please realize this is our call stack. This is also a stack. It works like the stack we're implementing now, but we only have one. The call stack, which is does not locate on the heap at all. So we store our return value on the call stack, right? Then we allocate 4 bytes to create a stack data structure on the heap. And so after this 2 lines, we have reserved 4 bytes in the heap. And A0 will have the address of those 4 bytes. So A0 will now have the address of our stack, the address of this top pointer. Since the stack is empty, we're going to store the value 0 at that newly allocated space. And never assume that when you dynamically allocate memory, that this memory is 0. That's a dangerous assumption. There could be stored memory, there could be stored values from different functions, and this memory might be freed and not cleared. So never assume an allocation function gives you zeroed out memory. Our allocation function never does it zero out memory. So we will store the value 0 in this top pointer, and then we have this empty top element. Then we are done. So A0 contains the address of our stack. The top pointer has the value 0. That's what is being asked in stack create. So now we just need to return. And how do you return? By restoring the return address from the stack, restoring the stack pointer since it's a call safe register, and returning to main. To the calling function. Stack create. Now let's look at the most complicated function of this exercise, and that's stack push. Adds a new element to the top of the stack. Now input arguments will be the address of the stack in A0 and the value that needs to be pushed on the stack in A1. So we have two input arguments, A0, the address of the stack, and A1, the value that we're going to push on that stack. So we will need indeed to allocate memory to store this new value. And right, so make sure to modify the top pointer to point to your newly pushed elements. So what's being said here, you will also need to allocate heap memory to store a reference to the previous top. So we need memory to store a value, memory to store a reference. That's what's being represented right here. These are 2 different squares of 32 bits. One stores the value, one stores the pointer. So when you push an element to a stack, you reserve these elements, which are 2 times 32 bits, 64 bits, 8 bytes in size. And the first 4 bytes store the value of the stack element, and then the next 4 bytes store the value of the next element on the stack. Now, let's think first of, imagine we created here 2 empty squares. How should we now modify everything that this is correct? Well, we're going to first store the value, or we can store the value of this new element. We can store that in the first 4 bytes of our allocated memory. And then to what will the next pointer of this new element point? Well, if you add a new element here to this stack, this will be inserted right here. So the value of next will be the previous top element of the stack. So top currently holds a value, but if we push a new element, top will point to our new element, and the next pointer of the new element will point to the previous top. So that's what we're going to do in stack push. Now, stack push has 2 input arguments. And it has, so it's going to call a different function. So before you can call a function, you need to make sure all the caller safe registers are saved on the call stack. So that's what happens here. We store our input arguments and our return address, all 3 caller safe registers. We store them on the call stack. Then we are ready to allocate our 8 bytes of memory for our stack element. We allocate those. And then now we're just going to make sure our new element, which is now reserved, is initialized correctly. So first we load the address of the top pointer in T0. So we stored the address of the stack, or the top pointer. We stored that on the stack. We backed that up before we called allocate space. This function might have overwritten the value in A0, but we know the stack value is still intact. So we know the address of the stack is located at 4SP. So we load that in T0. So from now on, the address of the stack is in T0. Now, since we're pushing a new element, well, we can modify this top to point to the new element. But before we do that, we need to make sure that we have this old top address, because this old top address will now need to be stored in the next field of our new element. That's what happens here. First, we load the old top pointer in T1, and then we overwrite this top pointer to point to our newly allocated memory, which is an A0 because of the allocate space function. So allocate space, allocated some bytes, the address is an A0. This address is now stored in the top, but before we overwritten the top pointer, we first made sure to store that old value in T1. Now we can initialize our element. So our new element has two fields, the value and the top pointer. So first, we can store this previous top pointer in the next field of our new element. Our new element is located at A0. The next field is at an offset 4 of A0. So A0 would contain this address, and then the next pointer is 4 bytes later. So that's where we store the old top value, which is now going to be the second element on the stack. The address of the second element of the stack. Then, only last thing we need to do is to actually store the value of our newly created element in this structure. So we load this from the stack. That's where we backed it up. We backed up A1 at 8 SP. And you might think, wait, but we never overwrote A1. The value is still an A1. You can't know that. Allocate space could possibly have overwritten A1. It's perfectly allowed to. So you cannot assume A1 has not been changed. So in this case, we load it to T1. We load the value 8 SP, which is the value that we actually wanted to push to the stack. And we store that value, so it loaded into T1, and we store that at the location of our new element. So at the value field. Then we're done. We've added an element to our stack. Now we just need to return from our function. We store the stack address, we store the return address, sorry, and then we store the stack pointer as usual. That's stack push. Now the last function, stack pop, is very, very simple after you've done all of this. So what does need to happen when you remove an element from the stack? So if you execute pop on this stack here, we will delete this first node, top will point to the second node, and the return value will be the value of the node we just deleted. How do you write this in code? Well, A0 will again have the address of our stack pointer. So now T0 will have the value of our stack pointer, which is the address of the element, which is the first element on the stack. T0 has the address of the first element after this line of code. That's the element we're going to delete, by the way. So what happens now is we overwrite our top pointer, T0. T1 will have the address of the second node. Oh, sorry. We go look. So we're popping here. We're going to look for the address stored in next, right? This is the address. So let's say we remove this node. We're going to find this address and load it into T1, because that's going to be the new value of top. Top will point to what's stored in next before the pop. So we load what's stored in next to T1, and then we let this value be our new top in the third line of code. The last thing you need to do is to make sure to actually return this value. So T0 had the address of that node we just popped. So if we dereference T0, we get the value stored in that node. We load that into A0, which is the return value of our pop function. And that's how we implement pop. So if we then look at this main function we created to test everything, we call stack create, which creates a new stack address in A0. Then we stored this address of our newly created stack. We stored that on the call stack, because we're going to call functions and these are not caller safe. We need to store this stack pointer since it's an A0. Alternatively, you could move it to a callee safe register. So just some options, but we stored it on the call stack here. Then we're going to push the value 1 to the stack. So A0 already has the address of our stack. A1 will take the element that we want to push. So this pushes 1 to the stack. Then we restore. So stack push might have overwritten the value of A0. So now we restore the value, the address of the stack in A0. We load the value 2 into A1, and now we push 2. We do the same thing and we push 3. So we pushed 1, 2, and 3. So we have a stack with 3 elements now. Then we're going to pop. So right here, load value A0 for SP. What are we doing? We're restoring again the address of the stack, which is nicely backed up at 4 SP. We restore that into A0 and we call gel stack pop, which pops the top element from our stack. So now we have 2 elements left on the stack, which is 1 and 2. We call pop again. And after this, if everything went correctly, we have a stack with 1 element and we have 2, the value 2 in A0 because we just popped the second element of the stack. Let's assemble and run and verify. So this is the address of our stack right here. This is our top pointer. Let's follow the top pointer. The top pointer is pointing to the value 1. And the next field of the value 1 is 0. So that's exactly correct. We have a stack with 1 element, which is the value 1. And that's the end. A0 indeed should have the value 2. That's the previously popped element. We could rewind a little bit here. Let's rewind until before the previous pop operation. So now we are rewinded just before we popped 2 from the stack. So let's now see the top pointer is now pointing to this field, which has a value 2. And the next pointer of this field is pointing to this field, which has the value 1. So we have a stack with the values 2 and 1, which is exactly correct, which is what the state should be before the pop. So there's your solution to the third exercise. A very good one, and if you completed this one, this is a very good preparation for the exam.